morning, doctor. We are from group 2. The mixture that we are going to present is water and ethanol. Okay, so I'll first introduce my group members, which is Saswan, Gatana, Pravin, and also me, Chan. The flash separation process is a technique used in chemical engineering and industrial processes to separate a mixture of liquids with different boiling points. It is a simple and cost-effective method that relies on the principle of vapor-liquid equilibrium. During flash separation, a liquid mixture is heated and then rapidly depressurized or flashed into a lower pressure vessel or separator. The sudden drop in pressure causes the more volatile component of the mixture to vaporize or flash, while the less volatile components remain in the liquid form. The resulting vapor and liquid phases can then be separated and collected. The separation is based on the fact that the vapor and liquid phases will have different compositions due to the varying volatility of the components. The more volatile components with lower boiling points will preferentially vaporize, while the less volatile components with higher boiling points will remain in the liquid phase. Flash separation is commonly used in various industries such as petroleum refining, chemical processing, and natural gas processing. It is particularly useful for separating hydrocarbon mixtures where different fractions like gasoline, diesel, and liquefied petroleum gas (LPG) need to be separated from crude oil or natural gas.
Before we start our calculation, we fix our temperature, pressure, and composition. The temperature is set to be 85.3 degrees Celsius. This because the normal boiling point Tn for methanol is 64.75 degrees Celsius, where normal boiling point for water is 100.15 degrees Celsius. So we took the temperature in between the range for our calculation. The operating pressure is set to be 85 kilopascal, which is below than 180 m. It is because we search in Google, mostly in industrial usage for flash separator, they maintain the pressure equivalent or below than 85 kilopascal, where it is reasonable for both fluid, methanol, and water. The composition for methanol is 0.22 and the composition for water is 0.78. The methanol is completely soluble in water. We need to separate methanol water mixture. Mainly, we need the methanol for the further process in industry. Thus, the percentage of methanol in the mixture will be less compared to the water. These are the assumptions we made. First, we assume the basis is 25,562.76 kilomole per hour fat mixture. Second, the mixture is ideal solution, so we can apply the Rolle's law for our calculation. Third will be the separation is 100% efficient and the flash column is well insulated.
Alright, moving on next to the pressure calculation. We were using the Antoine equation to find a vapor pressure for our substance, which is for methanol also and for water. As you can see in the slide here, this is the equation we will use to find the vapor pressure. For the value A, B, and C, these values are given in the textbook in Appendix B. Okay, for methanol, we are getting 216.36 kPa, and for water, we will be getting of vapor pressure of 58.56 kPa. Alright, for the next calculation, we will be performing the bubble pressure calculation. Alright, for the bubble pressure calculation, we will assume the Zi equals to Xi. X indicates the composition for each substance that we estimate at the early of the project, where 0.22 for methanol and 0.78 for water. Okay, vapor pressure for substance 1 as well vapor pressure for substance 2 have been calculated in the previous slide. So for the total bubble pressure, we'll be getting 93.27 kPa. Moving on next for the dew pressure calculation. In here also, we will be performing as the Z equals to the Y. Y indicates the composition for the two substances, which is methanol and also the water. So using this formula, we'll be getting the dew point pressure of 69.75 kPa. So since the total pressure lies in between bubble pressure and also dew pressure, the system is in two-phase region. So the flash calculator is possible. So using alright, so since this pressure lies between this bubble pressure and also dew pressure, we're able to calculate the K value. Okay, for methanol, for K1, the vapor pressure of substance 1 divided with the total pressure. Okay, this total pressure we have assumed in our starting of the project is 80 kPa. So we'll be getting K1 equals to 2.7045, and for water we will be getting 0.732. All right, that's all for me. Thank you.
So for the binary system, we can calculate the composition using Raoult's law. Raoult's law, which is X1 equals to P minus P2 saturated over P1 saturated minus P2 saturated. P2 saturated being the saturation pressure of water, and P1 saturated being the pressure saturated for methanol. As you can see, we can get the value of X1 equals to 0.1676 mole methanol per mole. And we can get the mole fraction of water, X2 equals to 1 minus X1. So we get the value of 0.8324. So for the next part, so to find the mole fraction of methanol, we can simply use the formula y equals to x times by k, where we can get the x value from the previous slide, which is 0.1676, and k, which has been calculated by my group mate Praveen, 2.5454, which gets a value of 0.4266 mole methanol per mole, which is 42.66 mole percent. We can also use the same method to find Y2, which is equivalent to 57.34 mole percent. As you can see here, we can get the value of mole of vapor, which is V equals to P bulk minus P over P bulk minus P dew. We can get the calculated value, which is 0.3516. So that is the mole of vapor. So to find the mole of liquid, we simply just equal to 1 minus V, which is 1 minus 0.3516. We get the value of 0.6484.
This is the TXY diagram for the process, where the y-axis is temperature and also the x-axis is x1 and y1. Well, this is the PXY diagram where the difference is only that the y-axis is pressure in kilopascal and the x-axis is also the same, which is x1 and y1.
This is our flash column. We have 25,562.76 kilomole per hour mixture consists of 22 mole percentage of methanol and 78 mole percentage of water. Enter the flash column. For the product, we obtain 353.823 kilomole per hour. Vapor consists of 42.66 mole percentage methanol and 57.34 mole percentage of water in the top stream, while 1956.936 kilomole per hour liquid consists of 16.76 mole percentage of methanol and 83.24 mole percentage of water in the bottom stream.